So, having observed experimentally that all of this is indeed possible, maybe now we can switch and see what happens in theory.
Sure.
Right? So, let's come back here. Okay. You have to help me write these equations, Ani.
Sure.
Okay. So, I have. So, typically, by the way, in in electrical engineering, we define what is known as a ground.
That's right.
That's
I think when Bobby and I were discussing it, we did mention it.
Yeah.
And we mentioned that there is an earth
Yes.
potential, which is the reference potential
Yeah.
for all circuits. Absolutely.
Correct. So, usually we will just say this is a ground
Zero.
node. I don't
Yes.
have to close the loop on everything.
That's right.
Right. So, this is a time varying signal. It could
V1.
be DC, right? V2, R1, R2 and R.
Okay.
Right. So, we are
Perfect.
going to see now what happens. Like I said, there is some current flowing out of this branch,
Okay.
some other current flowing out of this branch, and obviously what flows here is I1 plus
I2.
I2.
Okay.
Okay. So, what we'll do is, we'll apply KCL on two loops.
Okay.
The red one is one
Okay.
loop,
Okay.
okay, and the magenta one is another loop.
Now this is interesting. So we taught the students to do just independent loops. So now it is also possible to do mesh analysis with combined loops as well.
Exactly.
Because that's also a valid loop.
You have shared elements and those are independent loops by themselves.
Perfect.
Right? And KCL and KVL should be
valid among those loops as well.
Exactly.
Perfect.
Right?
Okay.
So you take the outer loop. I'll write the equations for the outer loop in red.
Okay.
Right? So essentially V1 is the source.
Yes.
You go on the right, you get V1 minus
I1 R1.
I1 R1,
right,
minus I1 plus
I2 times R.
into R equals 0.
Yes.
Okay. Similarly, if you look at the second loop, which is in magenta, V2
yes minus I2
minus I2 R2 minus same thing.
Yes.
I1 because it's going to the same resistor.
So yes. So interestingly, when we did learn mesh analysis, we saw that the shared paths terms occurred in both the equations.
Exactly.
In this case, the shared path is this I1 plus I2 flowing into that resistance R. That is the shared arm.
Exactly. And therefore, you see it exactly like this. Now, what do we want? By the way, we want the voltage on this node because that voltage is what we measured as a sum out here, right? So, what we want is Vx, which is nothing but I1 plus I2 into R.
Okay.
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 So, we need I1 plus I2. Essentially, that's the term that we are going to look for.
Yes.
So, I'll rewrite this term. Okay. V1 is equal to I1 R1 plus I1 plus I2 into R, and this other term V2 is I2 R2 plus I1 plus I2 into R, right? So now what do we want? We want I1 plus I2. So I'm going to divide by R1 in the first equation and divide by R2 in the second equation, right? So implies V1 by R1 is I1 plus I1 plus I2 into R by R1.
Yes.
Okay. And likewise V2 by R2 equals I2 plus I1 plus I2 into R by R2.
Great.
So now you can see that if I add these two equations, I will get I1 plus I2 in both of them. Now the color doesn't make any more sense, so I'm going to continue in black. So it is V1 by R1 plus V2 by R2, okay,
yes,
equals I1 plus I2 into 1 plus R by R1 plus R by R2.
Great.
Right?
Yes.
And now I have an expression for I1 plus I2 in terms of V1, R1, R2 and R, right? And therefore, I can write this as I1 plus I2 equals V1 by R1, V2 by R2, right? Divided by
1 plus
1 plus R by R1 plus R by R2.
Great.
Okay, and
Great.
what did we want? We have to, Vx is just I1 plus I2 into R, right? So we get V1 into R by R1 plus V2 into R by R2 divided by 1 plus R by R1 plus R by R2.
Okay, so now we can see that you are able to somehow add V1 and V2.
Yes, right. So I can now write this as alpha 1 times V1
okay,
plus alpha 2 times V2.
Actually, yes, because you mentioned that you want to scale different voltages by different amounts.
Exactly.
And I can clearly see that V1 is scaled by R by R1, V2 is scaled by R by R2.
R2.
So by choosing R1 and R2 and R, I can change.
You can change, and exactly that's exactly what you did when you tune that potentiometer. You were changing R2,
yes,
and thereby this net Vx got modulated by the appropriate. So let's just go back and see if these calculations make sense.
Yeah.
Right. So we had in our experiment, we had R equal to 1 kilo ohm, right, and we had R1 equal to 400 ohms, and R2 equals approximately 400 ohms actually, right, 390 ohms or something like that. And now what I don't remember is V1 was what, 1 volt,
1 volt,
and V2
was 2 volts.
Was 2 volts.
Yes.
Right. So we'll see how much Vx we got. Okay. So it is essentially.
So R by R1 and R by R2 are both
are the
about
same.
2.5.
Are exactly are right. Both about 2.5, right? So this is basically V1 into 2.5 plus V2 into 2.5, right? Divided by 1 plus 5.
Yes, 1 plus 5, which is
6.
Yes.
Right. So we got approximately, how much did we get? So if you take.
So V1 was 1 volt, right?
Yeah.
So that's 2.5 plus 5, 7.5 by 6.
Plus this was 2 volts, right? Yeah.
Yes, 2 into 2.5
by 6.
Yes.
So you got about 7.5 by 6, which was approximately.
It's
1.25, right? Approximately equal to 1.25 volt.
Yes.
If you remember, this is what.
Correct. In fact, that's what we measured as well.
Right?
Exactly. We gave DC voltages of 1 and 2 volts. We actually measured 1.25 volts.
Exactly. Right. So this is exactly what we got.
Yes.
And with the sinusoids also, it is possible to get exactly same this V1 of t. So if you go back and see, right, we said Vx equal to alpha 1 V1 plus alpha 2 V2, right? So this Vx, if V1 was the sinusoid, it would be alpha 1 into 1 volt.
Yes, 1 volt.
Sine of 2 pi f naught t plus alpha 2 into 1 volt into sine of 2 pi into 10 f naught.
Yes.
Right, 10 kilohertz.
Yes.
Right, and this is what we said was a sine plus sine. You could effectively, it's like a product.
It's like a product.
It's a product. So this is what we said. So this is what it is doing.
Okay.
Right. But in reality, don't we need the reverse?
Yes, you're right. Because we actually want to do the exact opposite.
Exact opposite, right? So in some sense, the guy sitting on the mixer is listening to the mix. He says, oh, the tabla is too loud, I need to adjust it. So he is going to go and adjust that resistor arm by some value so that it comes out correctly.
In fact, you remember I told you I had seen this in a Carnatic concert. The main vocalist actually had a way to listen to the mixing.
Yes.
So that he would tell the person, the audio person, to adjust it such that
correct. So in fact, that's called a feedback monitor.
Yes, that's right.
And in fact, the mix in that monitor can be very different from what the audience hears.
Oh, I see.
Because they need to sort of listen mainly to their voice, right?
That's right.
And if you look at a real concert, they will be like 10 different feedback monitors, one for the guitarist, one for the vocalist, one for the percussionist, and in each of them the mix will be different, the volume of the instruments will be different, so that they are listening to that and adjusting accordingly, right?
Okay.
So that's why if you look at this, the picture of this mixer, there are like volumes all over, right?
Yes.
You see many knobs here.
Yes, of
right?
course.
It's not, there is one master knob that you can push up and down.
Yes.
But there are multiple knobs here. Aux, it's called AX1, AX2,
yes.
right?
Yes.
That is to control different speaker outputs.
Speaker outputs.
So you can control the volume for each guy. So each speaker will get a different output.
Amazing. Amazing. Right? So this is a very sophisticated system.
It's a very sophisticated system. It takes 10, maybe 64 mics and gives out about 3 different outputs. And you can choose what the mix should be on each one of them. So the job of a sound mixer is absolutely non-trivial. It has to be done on the fly, right? And that's why it's mostly an analog mixer.
Yes.
Right? You will just see it's just simple addition like this and it just goes out. It's not, if you go to digital, you need to do some buffering and all that. It becomes a problem, right?
Yes.
But
by the way, now since you said addition, now I have a question. Can I also use this to subtract signals?
That is a great question. Do you have any ideas?
See, when we talked about Kirchhoff's current law as sum of all currents entering has to be equal to sum of all currents leaving. So maybe if I want to subtract currents, I should be able to do it, because all I have to do is change the direction of the current.
Okay, so what you're saying is we'll do this plus minus V1 R2
yes
plus minus V2
yes, yes.
right? Oh great.
So in fact if I do this, all I have to do is change that, because you are keeping the circuit the same.
Yeah.
You are just changing V2 to minus V2. I should be able to go back to my equations everywhere, just replace V2 with minus V2.
Yes.
I should get the answer.
Exactly. So in fact what will happen is you're going to have a current I1 here.
Yes.
And instead of the current flowing out, it will flow in to this branch I2. And therefore what comes out here
should be the difference
I1
between the currents.
minus I2.
Great.
So if you have like many such arms, one of them you could subtract.
Yes.
If you technically wanted to do so. Yeah, that's a great idea, right? So nice. But let's go back to our practical problem that we wanted to solve, right? What we actually want is we want Vx to be some particular value, okay? Beta 1 V1 plus beta 2 V2. This is what we want.
That's right.
Your given coefficients, right? This could be 0.4 or 0.6 and this could be 0.4. Right? This is what we eventually want. We need to choose resistors that actually give us
these values.
Yes. Right? So what we have to do now is go back. We saw that circuit gave us alpha 1 V1 plus alpha 2 V2, where alpha 1 was R by R1 divided by 1 plus R by R1 plus R by R2.
Yes.
And alpha 2 was R by R2 divided by 1 plus R by R2, 1 plus R by R1 plus R by R2. Okay. So essentially what I'll do is I'll call R by R1 as some x1 and R by R2 as some x2. Right. So that means I'm going to rewrite this as x1 by 1 plus x1 plus x2.
Yes.
x2 by 1 plus x1 plus x2. Now what we have is we are given beta 1 and beta 2. So we know that alpha 1 should be 0.6,
yes.
Alpha 2 should be 0.4, right? So all we have to do is go ahead and put this in. 1 by x1 plus x2 equals 0.6 and x2 by 1 plus x1 plus x2 equals 0.4.
So it seems like we have two equations and two variables x1 and x2.
Yes, and these are just two linear equations.
That's right.
You just multiply it and do it.
Yes.
You will basically get a system of linear equations, and if you solve that, you will find what the equation should be,
yes.
right? But an interesting point, you mentioned two variables, two equations. Yes, there are two x's and two equations. Fine. but actually there are three variables. There is R, R1, R2.
That's right.
Right?
That's
So
right.
what does that mean?
Do you think it's maybe because we want more degrees of freedom? Maybe we want to do. Can we increase the size using the third resistor?
Yes. You
So
could.
maybe we could.
Yeah. So in fact, the third variable R is a free variable.
Okay.
You can choose it.
Okay.
And in fact, in a practical system on a board, you have only certain allowed resistors.
Okay.
So it may be useful in some cases to fix R so that the R1 and R2 match practically available values.
Okay.
So that the ratio R by R1, right? So you could choose, if X1 comes out to be, let's say 0.3, R by R1 is 0.3, right? It could be 1 kilo ohm, 3 kilo ohm, or it could be 1 mega ohm, 3 mega ohm, it doesn't matter,
Okay.
right? But depending on the available resistors, you could choose this, right? And therefore, it's a good thing that we have that extra
degree of freedom.
Free variable, right? So effectively, this is how you will solve this entire problem. Like you mentioned, putting in subtraction is not a difficult problem here, right? We could always do it. Now, what I want to, show you is having, done this addition and, demonstrated this addition very nicely in both theory and practice, right? I want to bring your attention to a certain sequence of numbers. Okay, I want to do the following. Vx, okay, I want it to be in this form: B1, V1, B2, V2, B3, V3, B4, V4,
Okay.
plus B5, V5.
Okay. So you are going to need. Okay, the circuit is going to get quite complicated.
It's going to get quite complicated. It has 5 arms, right? Plus the 6th resistor arm, right? That I want. But it's a very interesting sequence of numbers that I want. I want 1 by pi.
Oh, okay.
B2 is 1 by 2 pi. B3 is 1 by 3 pi.
Okay.
B4 is 1 by 4 pi. And B5 is 1 by 5 pi.
Interesting. So when you connected up two sinusoids, you just scaled them up with 1 volt and 2 volts. So I just got scaled up values.
Exactly.
Right. Okay. So now
But
you are saying
not only that. Okay. I need V1 to be, let's say, 1 volt. I don't care about that. Right. It is, I will just call it sine of 2 pi f naught t. Okay. F naught is, let's say, 1 or 10 kilohertz.
10 kilohertz. Okay.
Okay. Some number.
Okay.
V2 is sine of 2 into 2 pi f naught t. Okay. So this is a 20 kilohertz sinusoid.
Okay. So in the experiment when we did, we added like a 1 kilohertz signal and a 10 kilohertz signal. So now what you are saying is add a add a 10 kilohertz signal and a 20 kilohertz signal.
20 kilohertz signal. And V3 is a sinusoid.
Let me guess.
Yes.
20 kilohertz.
Yes.
Okay.
V4.
So 40 kilohertz. No surprises.
40 kilohertz. And V5 is, let me put an arrow, 50 kilohertz.
Okay. Interesting.
Okay, this is a very specific sequence of signals that I am trying to add, right? Okay. And of course, in order to do this, it is possible to do it on the breadboard with resistors. There's no doubt about it. But you also have to, be a little careful about this because getting 5 sources and all that. It's
That's
just
a problem.
Bulky,
yes.
Right? Because this kit here gives us 2 sources.
Okay.
Right? So it was easy to do it with 2 sources.
We
therefore,
we now need to put in 3 kits and so on.
Exactly.
A little bit complicated.
Exactly. So I am going to now switch to what is known as a simulator. Okay, I am going to switch to a simulator, right? So this one, by the way, is just a very similar experiment that we did.
Okay.
1000, 400, 400.
It just looks like the mirror image of the circuit that you drew on this.
Exactly.
The resistor R is on the left side.
Right. Exactly. Right. And of course, this is R1, R2, and R3.
Yes.
Right. and you can add a voltage source which is a sinusoid or a DC or whatever, right? Simulators give you that freedom, and simulators are particularly useful to try out such complicated experiments first, get the values right.
Yes.
And once you are sure, you can then go to hardware.
Makes sense.
Right? So what
and there's no danger of burning up any components.
Exactly,
anything,
right? There's no money lost.
Money
it's
lost.
A software ultimately, right? So I'm going to open this. Okay, I have basically done essentially the same thing. Okay, I have 5 sources: V1, V2, V3, V4, V5.
So the original circuit that you drew had two V1, R1, V2, R2 in series, and
Yes.
you're combining the currents.
Yes.
You have just created the same version for 5 sources.
5 sources, right?
Okay.
They have 5 arms with the
Nice.
voltage resistor combination.
Voltage resistor combination.
And the currents will all add up into this R1 resistor.
Okay, so we are still using the same Kirchhoff's current laws at that node.
Same
at
thing.
the top of
It's
R1.
the same thing. It's only 5 different nodes.
Currents that are being
right?
added.
So what I'm going to do now is simulate this. Do a transient simulation of this.
Okay.
Right? And I'll run this. And of course, maybe all this I can close. And what I'm going to do here is I'm going to go ahead and add this trace here. I'm going to add a of Px.
Okay.
What does this?
This is the voltage at the top of the resistor, R1?
This is the voltage on that resistor.
The sum of the
sum of these.
all these.
So what is this voltage?
Okay, this looks interesting. So it looks like you're periodically climbing something.
Right.
That's what it seems like.
Exactly. Right.
If you go from the bottom to the top, you seem to be climbing.
So if you look at this voltage, it's sort of wiggly.
Yes.
Right? But it's jumping up.
Yes, or climbing down. Rather,
yeah. Right. And then it's jumping up.
Jumping up and then coming down again.
Right.
Yes.
But what is the frequency? It is similar to this 100 microseconds. Right. It is repeating after every 100 microseconds.
So every 100 microseconds, that's about 10 kilohertz, right?
It's
yes.
not surprising because that was our fundamental frequency that we
F0.
chose.
Yes.
F0, right? So
yes.
if you look at it, this is just the sinusoid with its harmonics.
Okay.
5 harmonics is what I've chosen, right? Or 4 harmonics. No, 5 harmonics.
Yes.
Right? So 10 kilohertz is a fundamental, and then you are getting an output which is periodic with the same 100 microseconds or 10 kilohertz.
Yes.
Okay. But if I observe this little more carefully, the best approximation that you would make, right, is maybe
yes.
I'll draw it on this.
Yes.
Is actually a straight line and simply something
yes.
that drops back.
Right. That's right.
Right. It goes up, it drops back.
I see. Okay.
You've seen this wave somewhere?
No, I have seen it in real life. When I did my undergraduate, we had to do carpentry. That's where I have seen this.
Yes, so absolutely. So this is, that's why it's called a sawtooth waveform.
I see. Okay,
right?
so it is used in a saw.
It's used in a saw.
I see. Okay.
And what you see here is absolutely not a coincidence.
Okay.
Right? Adding sinusoidal harmonics in a certain way with certain coefficients is what you call the Fourier series.
I see. Okay.
Right?
Okay.
Which of course, we will do for our students in this course later in signals and systems or networks and systems. But this is a circuit to implement a Fourier series.
Seems like a very powerful
yes.
idea, powerful concept.
Exactly. Right. And interestingly, in today's world, right, where we are talking about very low power and low energy evaluation, this concept of analog computing, which was very common in 60s, 70s, is now coming back. Right,
yes.
It is actually becoming a very popular technique. So it's useful for students to know this, these kind of computational techniques in the analog domain, right? But let me ask you a question. This is, related to your thing, right? I gave you all positive coefficients.
Yes.
But a Fourier series can have negative coefficients.
Yes.
What do we do?
In fact, if you have negative coefficients, you'll get a completely different waveform, I'm guessing.
Yes, you will get a
Right.
completely different waveform, but that's where your idea of subtractor comes
Subtractor comes in.
in, right? You just have to put in that particular harmonic the other way around,
The other way around.
right?
Yes.
But the resistor value is still
Is the same.
evaluated in exactly the same manner,
That's right.
right?
So it seems like you can synthesize almost any waveform that you want,
Exactly,
right?
right?
With positive, negative,
Yes,
and changing the value using resistors.
yes,
Seems like, in fact, I'm assuming that's what the audio engineer is doing when they're mixing.
exactly.
They are getting
So-
something very finely to what
Exactly.
is
They're
perfect.
listening to this and adjusting it till that mix sort of, is right. Okay. Of course, this, if you want to solve 5 equations, you will get a 5 cross 5, so
Yes.
it's better to do it as a matrix times something, invert the matrix
correct.
and find the solution, right? It can be done numerically as well. But do you see any catch in this?
Well, it's getting very complicated very quickly.
Of course, but
Right.
in terms of the numbers that we have chosen, have we conveniently chosen certain numbers in a certain way?
Yeah, we seem to have chosen something related to pi, right?
Pi, of course,
Of course.
but
And also we have chosen the frequencies such that they are all multiples of each other.
absolutely. So that
Right.
comes from the Fourier series.
Fourier
But
series.
I'm talking of, something more. You look at, what do you think the range of alpha 1, alpha 2 could be?
Yes. Okay. From what I can see, you have chosen 0.6, 0.4.
Yeah.
Alpha 1 is R by R1. Oh, okay, I see it.
What?
So both alpha 1 and alpha 2 are both less than 1,
Exactly.
right? Because irrespective of what I choose for R1, R2, it seems like both alpha 1 and alpha 2 are always smaller than 1.
Right. So in fact, this is what I think you discussed earlier. These are passive elements.
Yes.
Right? They cannot amplify a signal, right? So in some sense, what we have done is, relative to the voice, you could adjust the other things, but I still cannot amplify the whole thing.
That's right.
Right? To amplify, you need active devices, which we will look at in the next lecture.
So in fact, there is, in sound systems, I have seen a mixer and there is a separate amplifier.
Exactly.
Right? So I'm assuming that the two things functions are completely different.
Exactly. In fact, if you look at those speakers, right, they are so large that they cannot be driven with simple voltages. They need really high voltages. So you have to amplify that significantly, right, and drive those speakers in live concerts.
Yes,
right?
I can imagine.
So, that is one aspect, right? But I'd also like to bring your attention to this whole equation when we wrote it. You see this equation here.
Yes.
This seems to have some significance. V1 by R1 plus V2 by R2.
Yes.
V1 by R1 seems to be some current if
That's right.
the R1 was connected across V1.
That's right. Yes.
So, is there any trick? Is there any other way that you could solve this equation?
So, it seems like you have two components, right? I1 and I2. It seems like if you did not have one voltage source, that current would become 0.
Absolutely.
Right?
Right. So, I think this is a great technique, and in the next lecture, we will look at how you can alternately solve this same kind of an equation.
Yes.
In a method called the superposition, principle of superposition, and that is a very easy way of solving a circuit like this. Thank you.